Admitting everyone, and we are now on the live stream.
Okay. Welcome, everybody. It's a great pleasure to see all of you for another Robotics Institute live talk. Today, Carlo Sferrazza is talking about data-driven, vision-based tactile sensing, design, simulation, and applications to robot control. Carlo is a PhD candidate at the Institute for Dynamic Systems and Control at ETH Zurich under the supervision of Professor Raffaello D'Andrea. So we are kind of family in terms of the academic history. And his main research interests include the design and development of vision-based data-driven tactile sensors and the applications of those sensors in robotics. He received 2 bachelor's degrees, one from Politecnico di Milano and one from Tongji University in China. And then he joined ETH Zurich for a master's in robotics systems and control. And he has already received a number of awards, in particular the Best Paper Award at the 2020 IEEE International Conference on Soft Robotics. And he also received the 2017 ETEL Award for his master thesis on model predictive control for UAVs. He has spoken at a number of general public events such as World Minds and TEDx Zurich. So I'm really looking forward to his talk, and I hope you enjoy the talk. Feel free to post questions both on the YouTube live stream as well as on the chat on Zoom, and we'll get to those at the end of the talk. So welcome, Carlo.
Thank you very much for the introduction. It is a pleasure for me to be here, even if virtually. So I believe that robots need a dexterous sense of touch to address most of the interaction tasks that they're going to face and that involve physical contact. And this would enable a number of applications, so from warehousing to entertainment, from human-robot interaction to medical devices. And in this context, in the last 5 to 10 years, we have seen an incredible growth in the development of high-resolution tactile sensors for robotics applications. And these tactile sensors can be based on a variety of different principles. For this reason, I believe that now more than ever, we need to extract intermediate representations from the raw tactile data, such that the techniques and the results could be reused and reproduced even when not the same tactile sensors are being employed. And this will be one of the main messages of my presentation, as I will detail later in the talk. But let's take a step back and with a short introduction, see what we generally mean with sense of touch and try to understand the importance of the sensory feedback in humans to possibly extract some requirements for robots. You may have already seen this video where a woman has had their fingers anesthetized, and therefore she can only use her sense of vision, her sight, to perform a very simple task as striking a match. And she's having a very hard time just because she misses the dexterous information usually provided by the sense of touch. If we instead look at robots, the very traditional way of getting touch or contact feedback were force torque sensors. However, these sensors are pretty bulky and they are stiff, so generally they are only used in the robot wrist. Therefore, when interacting with the environment, they only provide information about the forces acting at a single point, usually at the center of the sensor. In contrast, I'm going to show you 2 examples of how the human sense of touch is much more capable than this, which has motivated the increasing development of modern tactile sensors. First, we have soft and dexterous hands, which provide us with stable gripping when we handle an object, exploiting, for example, the high compliance and the friction of our skin. Additionally, our receptors can very well detect and distinguish between shear and pressure forces, even when they are simultaneously applied over the skin. Finally, our receptors are not limited to specific regions, but distributed all over our body. And this in particular allows us to perform difficult tasks, as when we do not only use the hands, but also the legs and our chest to lift a heavy box. So we have these sensors, our receptors, that are placed all over the skin, which means over different types of surfaces, which can be either curved or flat. So using these capabilities as an inspiration, I'm going to describe a vision-based tactile sensing principle, which especially tackles the requirements of high resolution and scalability. The sensing principle is based on the tracking of particles within a deformable surface. So for this, we use a camera, which we place inside this aluminum part, and we surround it with LEDs for constant illumination. On top of the camera, we place 3 layers of silicon. A soft and stiff layer that is transparent and serves as a base for the other 2 layers. Then we have a very soft layer which embeds green particles, thousands of green particles that serve as markers. Finally, we have a black layer that covers the sensor and shields it from external disturbances. You can see here the final design of the sensor where the 3 layers of silicon are poured on top of each other sequentially. Now here you can see the sensor in action, and upon deformation, the particles start to move and create different patterns that are captured by the camera. The randomness of the particle distribution facilitates manufacture, and their denseness makes it possible to extract tactile information at each pixel of the images. The technique I described does not assume the surface to be necessarily flat, as in the case of the sensor that I just showed. In fact, we've also built sensors with slightly curved surfaces, for example, to resemble fingertips, or sensors using multiple embedded cameras, as in the one on the right, where we used 4 Raspberry Pi cameras to achieve at the same time a reduced thickness and a larger surface. All these sensors were fabricated at the same way without any special adaptation and rely on the exact sensing principle, proving the easiness in the scalability of the approach we proposed. So the sensing principle provides raw tactile data in the form of pixel intensities. But how can we further process the pixel information to extract an intermediate representation that can act as a powerful abstraction to plan generic robotic tasks? So looking at most of the tasks, we are generally interested in total forces, both shear and pressure forces, and contact patches, which are the surface regions in contact with an object that provide, for example, information about the shape of the contact object. And we want to estimate these quantities for arbitrary contact conditions, so possibly for multiple points of contact and for interactions with objects of different shape. And if we manage to do all of this in real time, we would then have a very powerful sensor which will truly provide the rich information ready to use for generic tasks. With this requirement in mind, we decided to move towards the estimation of a very comprehensive quantity, which is the 3D contact force distribution. And in fact, from the force distribution, one could compute the total contact forces by simply integrating the distribution over the sensing surface. And one could retrieve the contact patches by detecting the regions where the distribution is greater than 0. And this representation remains valid for the different possible contact conditions, therefore multi-contact, arbitrary shapes, and so on. However, since we want to estimate a finite dimensional quantity, we need an additional step. For this reason, we discretize the sensing surface over a finite number of bins and compute the force distribution as a set of 3-dimensional vectors indicating the force acting at each of these bins. So it means that if we make contact with a test object that has multiple points of contact, for example, 2 in this case, we get this image that is to some extent interpretable to a human observer if you can spot sparser regions in the marker distribution here. But we want to further process it and extract a 3-dimensional force field out of it, as you can see here at the bottom. So here we used 400 bins, where the side of each bin was about 1.6 millimeters. And we want to be able to sense contact locations, but also the force profile. Here you can see a higher force in this point, for example, since this finger-shaped body at the top was going deeper into the material than this other one. Therefore, summarizing our task, we have tactile images as inputs and discretized force distributions as outputs. We try to reconstruct these outputs, the force distribution, from the images observed at each time step. And we do this in a data-driven fashion, since such an approach can theoretically exhibit arbitrary accuracy, depending on the data provided. Essentially, compared to model-based methods, we don't have to compromise accuracy by making model simplifications to retain real-time tractability. But we just need to provide very accurate data. And additionally, data-driven approaches generally show very fast inference times, especially if we make use of tailored learning architectures. Of course, we need to collect training data, and I'm going to show you how we can do this in the next slides. Okay, consider a very simple case where we have a point indentation. So an indentation with a very sharp contact object like a needle. And assume that we do vertical indentations and we only have vertical force, so we can neglect horizontal forces. Now, if we can measure such vertical force, for example, with a ground truth force torque sensor as the one I showed you before, then we can actually measure the contact force F. And by discretizing our surface into bins, we can assign the force F that we read this bin here in the center and 0 to all the other bins where there was no contact. In this scenario, we can even automate the data collection. For example, if we attach such a needle indenter to the spindle of an automatic milling machine, we can then also attach a force torque sensor here at the top, and we can perform thousands of indentations with such a needle-shaped indenter by moving the spindle all over the sensing surface. In this way, we can collect a fully experimental datasets where we have tactile images captured during the data collection from the internal camera and force values that are recorded by the ground truth sensor. However, in a general case, we have multi-bin indentations. So we have indenters of arbitrary shapes that do not cover only a single bin, but they cover an arbitrary number of bins. And we want to estimate a 3D force distribution, so comprising both pressure and shear forces. The issue is that we do not have commodity sensors that can accurately measure the force distribution in the real world. So to overcome this issue, we perform in simulation the same indentations that I showed before with the automatic milling machine, but this time we do it in a finite element environment. And for this, we represent our sensor with very accurate hyperelastic models, which we obtain by a state-of-the-art material characterization experiment, so which you can see an example in this video. So for each indentation in the finite element simulations, we extract the three-dimensional force distribution, which is represented as a set of 3D vectors for each node of a fine mesh. You can see the nodes of the mesh in green here. And we obtain a discretized ground truth force distribution by summing the nodal forces inside regular bins that you can see, for example, here in red. And since this is actually the best we can get, we can assign such a ground truth label to the corresponding images that we can capture on real-world experiments, for example, with an automatic machine. Of course, we anyway verify the accuracy of the labels on what we can actually measure in the real world with commodity sensors, the total force. So essentially, we compared the total force obtained from FEM with the total force measured by an FT sensor in the same experiment. We first tuned our friction coefficient with a single shear experiment made with a spherical 3D printed body, on which you can see the good agreement between the FEM and the real world readings. What we did here was to apply pressure with the contact body and then translate it horizontally and measure the horizontal force at discrete steps. And even if we tuned on a single experiment, the model generalizes well also to other materials. See, for example, the contact with a stainless steel indenter, a much smoother material than the 3D printed one. And the reason for this generalization is that our sensing surface is quite sticky, and this dominates in the contact pair. Obviously, there is a performance degradation, but we still obtain an accuracy of around 10% of the maximum force. The model generalizes well also to other indenters. You can see here a shear experiment with a square flat object. And here you can see a pure vertical indentation, but with a multi-contact body that resembles two fingers pressing on the surface, again obtaining a very good agreement also on the vertical force. Therefore, the labels seem to capture the right trends. And summarizing, we could create a dataset where the features could be images collected in the real-world experiments, and the labels are ground truth force distribution obtained by finite element simulations of the same experiments. Here we have several issues. The first is that we have data pairing problems because we have data coming from different domains, the simulation and the real world. And this requires very careful alignment, for example, of the reference systems when collecting this data. And this is kind of tricky to do, especially when we deal with soft materials. Also, we still need to collect a lot of real-world data, and these data are dependent on the sensor that we fabricate. So therefore, we would need to do it again. We collect new data again every time we build a new sensor. So we asked ourselves, is there a way to get rid of this consuming data collection and do everything in simulation? Well, we can do this, and for for that, we need to simulate the tactile images as well. And we can do this by first sampling the displacement field obtained as well in the FEM simulations. So what we have to do is to account for the fact that the displacement field we obtain from the FEM is given in a frame which can be not centered with the camera. Therefore, we need a usual transformation described by a rotational matrix and the translational vector from the frame of the FEM to the reference frame of the camera here. Then we assume that the camera is an ideal pinhole camera. And this is a strong assumption, but allows us to make a closed form projection of these fictitious spherical particles to ellipses onto the image plane. And you can see the result here. On the right, these are synthetic images that are processed or generated during simulated indentations, as you can see here on the left, with different contact objects. And so in the end, we can collect a data set, which is made entirely of synthetic tactile images that we can express as two-channel tensor. Two channels because the first channel contains an image which is taken before deformation, and the second channel contains the image after deformation. You can see here the sparser regions that arise after deformation. And at each of the samples in the data set, we randomize the distribution of the markers, and in some cases also the density, as you can see, the density of the markers, as you can see in here, it's a bit of sparser distribution. So summarizing, we finally have both features and labels from simulation, where features are raw tactile images that are run with distribution of the markers that is randomized, and all these images are obtained from finite element simulations. The same finite element simulations provide us the labels, our ground truth for distributions. But since these data are valid in the simulation domain, how can we make sure that whatever mapping we learn from this data also works in reality? For this, we need an additional step, which is camera calibration. Essentially, we need to take some pictures of a predefined pattern to extract the camera model. And since we use our camera through a silicon medium, we need to do the calibration also through silicon. So essentially, what we do is to collect 6 images of this predefined grid pattern through some silicon shapes. And by using a state-of-the-art calibration technique, we can obtain both the intrinsic and extrinsic parameters of the camera with a sub-pixel accuracy. Finally, we use the model we obtained from calibration to remap the images taken in the real world as if they were shot from the ideal camera that we used in simulation. And this is a crucial part because we can redirect any instance of sensors that we fabricate to the same pinhole camera model. And this adds a lot of benefits to collecting data in the pinhole camera frame. So this is how remapping works. For each pixel in the ideal pinhole camera, we can project it through the 3D world by making the assumption that the particles have a fixed vertical coordinate. And then we can project back to through the calibration parameters to the real world image to find the corresponding pixel. Looking more in detail, we do first a 2D transformation from this P point to this S point in the 3D world, where the vertical coordinate again is considered to be fixed. Then we do a coordinate frame transformation to bring everything in the frame of the real world camera, and then we can obtain this point Q with this function that is given by the calibration toolbox that we employed. This is the result of the remapping procedure, and you can see here we have a sensing, a square sensing surface as I showed you earlier, and you can see that the distortion present in the original image is eliminated, and the sensing surface finally occupies a square image. And if we compare it with the left image, this is a synthetic image generated by our FEM simulations. Of course, there are differences due to unmodeled effects, but you can see that we're kind of going to the right direction. So summarizing, we now have tactile images as inputs and ground truth force distributions as outputs, both obtained by finite element simulations that we can use to train a data-driven approach. To evaluate such an approach, what we do on the real-world sensor is to just collect some images during contact, perform the remapping, and predict the current force distribution. So using only the simulation data, we train a tailored neural network architecture based on a slimmer version of UNet, a very powerful architecture often used, for example, in image segmentation. The network is based on a contracting path where relevant features are extracted from the images, and a decoding step where the force distribution is computed through upconvolutions and concatenations of the high-resolution features extracted during the contraction step. As a result, the architecture has the effect of both capturing the intensity of the forces and enabling precise contact localization. The training data consisted of simulated indentations with about 20 indenters. And in order to increase the robustness of the training, we perturbed the images by adding some salt and pepper noise and altering their brightness during training. After training, we then evaluated the network on a series of indentations that we collected in real-world experiments with several contact objects. And the network retained high accuracy on real-world data on all the components of the 3D contact force distribution. The inference of the force distribution runs at 120 Hz on the CPU of a standard laptop, with the limiting frequency being the frame rate of acquisition of the camera. Let me stress again that an additional benefit of the simulation training is especially that we do not need to retrain our network for each real-world sensor, but we only need to extract the camera calibration parameters for each sensor instance that we fabricate. More illustrative results. If we look at a specific sample, on the first row, you can see the ground truth resulting from a shear indentation in a y direction, following pressure, of course. And the real-world prediction matches this quite well. And you can see, for example, this asymmetry in the y direction, indicating shear, and the symmetric structure retained in x, as well, of course, as the contact patch in the pressure distribution. So if this was the comparison with the FEM ground truth, if we look at how the prediction compared with a force torque sensor in terms of the total force, you can also see a good agreement over time, where the solid lines here are the FT sensor measurements, and the dashed lines are the predictions. Again, you can obtain total forces by summing the respective component of the force distribution over the whole surface. Here we have a shear indentation with a cylindrical indenter, while here we have pressure with a triangular flat indenter over two different depths. The largest imperfections that you can see here, for example, are mainly due to the very large deformations introduced by the flat triangular indenter, which, however, do not hinder us from capturing the actual. Finally, even if we only train the neural network on data consisting of a set of specific contacts, the convolutional structure of the network shows generalization capabilities when applied also to generic objects, as well as in the contact with multiple bodies, a case which was not present at training time. So drawing an outlook on this work, let me point out that the current simulator is static, so it neglects all the dynamic effects that can be maybe of interest for some certain applications. And in addition, we only consider a fixed friction coefficient, as I showed you earlier, tuned with one indentation. It worked well across several materials that we tested, but if a more accurate estimation of the friction coefficient would be necessary, then you would need to identify this coefficient, for example, over time from different frames of the tactile images. Finally, here we focused on building a very accurate simulator such that we could achieve a seamless transfer from simulation to reality. However, one could think, for example, of using domain adaptation techniques that explicitly aim to reduce the gap between simulation and reality. So the next thing we asked ourselves is, how can we use this powerful physical representation as the force distribution that we can now estimate with our sensor to achieve dynamic tactile control tasks? So we wanted to design a testbed that was at the same time low-dimensional, but representative of the problems encountered when dealing with contact in a generic manipulation scenario. We also wanted our system to be capable of highly dynamic motions, for example, to trigger complex behaviors that are often neglected when one performs slower manipulation tasks. Therefore, we built a system that resembles a classical inverted pendulum, but without a mechanically fixed pivot point. This means that we want to grab a pole and swing it up to a vertical position without having the pole physically attached to the gripper. More in detail, the system is based on a linear motor that we call a cart that displaces the gripper over a stator. And if we look at an explosion view of the gripper, this is actuated by a servo motor, a dynamixel, and mounts two fingers equipped with two of our tactile sensors. And the sensor used here is the one I showed you earlier in the talk, where with a slightly curved surface to recall a fingertip. Therefore, summarizing the system architecture, we have two control inputs, which are the cart acceleration and the gripping distance. And we have sensory feedback about the system, namely the cart position and velocity, and the force distribution that we measure with our tactile sensors. Everything runs on embedded platforms. A Raspberry Pi sends the commands to the actuators and reads the cart position and velocity from the linear motor. And an NVIDIA Jetson TX2 is employed to predict the force distribution with our tactile sensors, as well as to run most of the control algorithms that I will describe in the following. So for this reason, the two devices communicate via Ethernet, exchanging all the relevant information. The sensors employed here predict the force distribution in a very similar way, as I explained earlier, with a data-driven model entirely trained with simulation data. So let me instead focus more on the control problem. And here, the main difficulty is given by the fact that contact dynamics and soft materials are very hard to model analytically. Therefore, learning from data seemed to be an appealing alternative to overcome this issue. However, learning on such a system is really time-consuming because you either need an automatic collector system or you need a very dedicated operator that takes the pole and brings it back to the original position every time that it flies away during data collection. So for this reason, we shifted our focus towards obtaining policies in simulation using deep reinforcement learning algorithms. So let's look at what we need from a simulator of the system. Well, first, we would like it to be general purpose such that it can be extended also to different use cases. Then we want it to generate sensible sensor output, the force distribution in our case, while retaining computational efficiency. Finally, a common technique to tackle the sim-to-real transfer consists in randomizing the simulation parameters to increase robustness in the control policies. Therefore, we want our simulation to be modular enough such that we can perturb these parameters during training. All these requirements can be satisfied with a strategy that is based on the finite element method, with the simplification that the materials are assumed to be linearly elastic. So how does this simulation work? Well, first we simulate everything at the level of the forces. And this is made possible by the fact that our sensor already outputs force values. Therefore, we do not need to simulate the optics, which facilitates the system modeling. The material model is also simplified, as I mentioned, by relaxing the hyperelastic assumption and assuming the materials as static linear elastic. This is a very strong assumption, but turned out to be enough to capture the trends of the force distribution in the simulations. Based on this, we developed a finite element direct stiffness approach, which we augmented with an iterative calculation of the friction forces. For this, we first mesh our sensing surface, dividing it in a series of finite elements. The method then works in two steps. First, we identify the forces arising from frictionless normal indentations. For this, we divide the nodes of the mesh in three sets. The figure here shows the nodes as dots spread over the sensing surface in green. Then we define the set C as the nodes in contact with the pole. So these nodes here, for example. Then we have the set F that contains the nodes in contact with the base. And then we place all the remaining nodes in the set N. Well, it turns out that we know something about each of these sets. For example, we know that the nodes in the set C stay attached to the pole. And if we assume them to stay in contact with the pole and displace vertically, we know everything about their displacement. Also, the nodes in the set F, they are attached to the rigid base of the sensor, therefore they do not move. And the remaining nodes have no external forces applied on them. In this way, we can finally apply direct stiffness, which is based on a stiffness matrix, K, that can be built offline in a finite element environment and is constant only for linearly elastic materials, therefore our assumption. This matrix relates the nodal forces with the nodal displacements. And for each node, we either know the displacement or the forces. Therefore, the system of equations can be solved very efficiently to calculate the remaining unknowns. The forces F0 obtained here consider a frictionless contact, so the next step is to account for the presence of friction. We do this in an iterative way, that is by first assuming that friction force is only unknown at the one node that we call I. Then we compute the friction force at a node I, assuming the Coulomb friction model. I will show you more in a second. Then we repeat this procedure for all the nodes and iterate until we converge to a certain value or for a fixed number of iterations. Finally, we sum the resulting friction forces FF with the forces resulting from normal indentations, as we computed in the previous step, to obtain the forces F that are used in our simulation to simulate the system by propagating them through the forward dynamics, where we use a semi-implicit integration scheme, such as in gaming engines or in simulators like Mujoko. But we also use the distribution of the forces F to generate the synthetic sensing output as well, our force distribution, which can be obtained again by discretizing the sensing surface. Now I'll show in detail what we actually do in these two steps to compute the friction force at one node in the current iteration using Coulomb friction. So obviously we need to compute the friction force only at the nodes in contact with the pole. So first we compute the relative velocity at the node I with respect to the center of the sensor. And this means that we subtract the velocity of the stator from the velocity at the node, which we can compute using the velocity of the pole, its angular velocity, and the position of the node. What we are actually interested in is the relative velocity at the next time step, because as I mentioned, we use a semi-implicit integration scheme, and it is standard to always employ the next step velocity to achieve better stability. We can express the next step velocity with this equation here, retrieved via this previous equation and the equation of motions that we use to simulate the system. So going through each term, this is again the relative velocity of the current time step. This is the velocity of the car, the acceleration of the cart, sorry. These are the forces in x and y components at the I node, which can be, again, divided as the forces deriving from normal indentation and the friction forces that we want to compute. These are the same forces, but at all the remaining nodes, called here J. And these two matrices here contains, for example, information about the physical parameters and the position of the nodes. Now, in this equation, we have two unknown quantities, but assuming static friction, we can set the sliding velocity to 0 and compute the friction force by solving the equation. However, we need to verify that the friction force respects the friction constraints, where this value here is computed from the normal, from the forces estimated at the previous step. And so if this friction constraint is satisfied, then we are done with this node and we proceed with the next. But if this is violated, we need to go back to the previous equation, where we again have two unknowns and we do not know how to actually decouple these two quantities. So we therefore use an approximation and neglect the contribution of this node to the overall sum. So this approximation is in general not too bad, because we use over 500 nodes, and the overall contribution of this node here is usually not too large in average when we consider this entire sum here on the right. So based on this, we can compute the relative velocity at the next step, and then using Coulomb friction law, we can compute the friction forces at the node I. Again, these forces are then summed to the respective forces stemming from normal indentation and computed in the first step. And in this way, we can obtain the three-dimensional contact force distribution, which is the same quantity estimated in the real world with our tactile sensor. So you can see the result here with a comparison between the forces predicted in the real world versus the simulated sensor output. And the simulation is very efficient and runs at 360 Hz on a single core of a standard CPU, which means 6 times faster than real time. We can then use such an efficient simulator to tackle the control problem in simulation using deep reinforcement learning. As a requirement, we would like to swing a pulse of which the physical parameters are unknown to the policies. However, this breaks the Markov property assumption because we introduce additional unknowns in the system's dynamics. Additionally, state information is incomplete on the real system or only indirectly available. In fact, we don't directly measure, for example, the pose of the pole, but we can only indirectly observe it via the force distribution measurements. For this reason, we take a privileged learning approach where we first exploit the full knowledge of our system in simulation. We therefore define an augmented state x prime of k here as the concatenation of the system state with the pole's physical parameters. Then an expert policy is trained using an off-the-shelf reinforcement learning algorithm, where the physical parameters of the pole are randomized at each new episode during training. In this way, the neural network that parameterizes the policies chooses different actions based on the features of the pole. The policy is optimized by maximizing an expected reward, which depends on the privileged information about the augmented state, and aims to swing up the pole by performing this 180 degrees rotation while maintaining low slippage. You can see here the results of the training with the expert policies that is able to consistently swing up poles that differ for mass, diameter, and length. Finally, we develop a student policy, which is trained as well in simulation to learn to imitate the expert, and to exploit the fact that the poles and the parameters of the pole are observable via the force distribution measurements. However, since the Markov property is not holding, we need the policy to reason over time. We therefore define an observation O of k as the concatenation of these four quantities, so the cart position and the gripping distance that we can read from our actuators, the pole orientation that we can estimate from our force distribution readings, and the normal force, the total normal force, which can also be computed from the force distribution. We then concatenate the last t observation to obtain this quantity here, OT of k. And finally, the policy is optimized by minimizing a stochastic loss where the labels are obtained by curing the expert policy for the visited states. So to summarize again, all the training happen in simulation. An expert policy exploits privileged information from the simulation to train a reinforcement learning agent that predicts the optimal action to achieve the task. Then a student policy is learned in the simulation to imitate the expert, simply observing an history of measurements, namely the actuator states and the force distribution, without any direct knowledge of the physical parameters. These measurements are all available in the real world, and that is why we use the student policy on the real system. So we directly deploy the policy without further adaptation, and its robustness makes it possible to swing up poles of different length, diameter, and mass with a pure feedback policy without the use of any feed-forward tear. But let me stress the fact that the feedback here is indeed crucial to solve this task. In fact, the actions depend on physical parameters that are unknown to the real-world policy. And the same actions also depend on the initial configuration of the pole that can differ across trials. And even if these two sources of uncertainty were to be eliminated, it would still be very challenging to achieve such an accurate set point tracking as is shown in this plot for repeated trials. Looking also at failure cases, this table shows experiments with 4 different poles where we aim to perform 10 successful swing ups with each of the poles. You can see that for the successful test, we had a comparable final errors in the order of 5 degrees. Pole 2, the longest, was even slightly outside of the training distribution range. However, we noticed a higher failure rate with pole 1, and I've tried to give you some intuition about the typical failure case. Essentially, our simulation underestimates an effect that we observed in the real world. So what happens is that when clamping, our material shows a relatively strong spring effect that makes the pole bounce back from the vertical position. So the cart tries to correct it by providing the right acceleration that you can see here between 0.5 and 1 second. However, for short poles like pole 1, we need aggressive accelerations to achieve the same desired torque. In some cases, this makes the motion become too jerky, and then we lose grip of the pole. So this approach is relatively successful with the swing up, but can it work for different tasks? It turns out that by tweaking the reward in simulation, it is possible to achieve different motions, such as a throw and catch maneuver. Of course, replicating this motion on the real system requires addressing other issues, as the non-planar motion of the pole during the flight phase, but the estimator could easily be extended to account for these effects as well. So let me draw an outlook to mention where I think we are and where we are heading with this work in the direction of dexterous manipulation. Well, first, this system achieves a rotational motion of the pole without directly controlling a rotational degree of freedom. Therefore, this is only made possible through the presence of friction. And for this task, as for many others, modeling friction is crucial to design realistic simulators, and this will remain a very relevant aspect in addressing manipulation tasks. The simulation approach I presented only used the fact that the pole is cylindrical when dividing the nodes in different sets, as I showed you earlier. But the approach can be extended to various geometries via the use of efficient algorithms that solve the intersection between polygons. Finally, we knew that for this task, angular and total force were key to perform the swing up. And therefore, we used those as part of the history of observations. However, for different tasks, it could be beneficial to design algorithms, for example, based on autoencoders, that could automatically discover the meaningful intermediate representations from the force distribution readings to further improve the generalizability of the approach. I will conclude remarking the main messages of this talk. First, high-resolution tactile sensing can largely benefit from physical intermediate representations, which can be used as an abstraction to plan generic robotic tasks. We demonstrated this on our tactile control testbed, where we showed the potential of tactile sensing to achieve dynamic manipulation tasks. We wanted to show that tactile sensing can enable tasks that are very challenging for humans to perform without vision. But in the future, it will be important to also include vision in the loop to improve efficiency and performance in a sensor fusion fashion. Finally, for both the points above, I believe that accurate simulations were and will be crucial to learn high-dimensional policies or robots that can make use of high-resolution modern tactile sensors. With this, let me thank my advisor, Professor Raffaello D'Andrea, and all the students that I've supervised at ETH that have contributed enormously to all the work that I've presented. Thank you for listening, and I would be very happy to take any questions that you might have.
Thank you so much, Carlo, for this very interesting talk that ranges from hardware design to deep reinforcement learning. So anyone on the Zoom, you can post questions in the chat or raise your hand. And if you are on YouTube, you can post questions right there. So I'll start with one question from the audience, from Philippe Nadeau. He was wondering, how often do you typically need to calibrate the sensor? Does the particles move over time with use?
Yeah, that's a very good question. And the answer is that before this happens, usually the sensor wears. So these materials, this is an issue with soft materials that they wear over time. So usually what happens is that either the material kinds of wears and there is some abrasion, for example, on the surface that doesn't allow us to estimate the force with the same accuracy as before, or the material ages, which means that, for example, it becomes harder or stiffer with time. And in that case, we don't have currently a model that accounts for aging effects. So usually what we do is, again, change the gel. But changing the gel is kind of a very easy procedure that takes less than a couple of hours to make a new one, I mean. But there are procedures also that allow you to just change gels. And you don't need to recalibrate the sensor after changing the gel. You can use, again, the same model because the camera is the same and the camera calibration parameters remain the same.
That's great. Just a follow-up question for me. What does it mean? How often do you have to change the gel?
Yeah, so for what regards aging, we have observed that usually after a month at room temperature, it starts to, you start to see like a deterioration in the force estimation if you compare it with a force torque sensor, for example. Mm-hmm. For what regard to wear is very hard to say. The swing up task, for example, is very demanding in this sense because you have always this motion between the two sensors and the pole. But usually we manage to run it, I would say maybe hundreds of times before we get a hole that is big enough to compromise the problem.
Okay, great. We have one question from YouTube. And the question is, do you think that these soft tactile sensors have like potential long-term, I assume long-term in applications, And do you have faith in the long-term practicality of IPMCs?
What is the last one? The last question again?
Do you have faith in the long-term practicality of IPMCs? I'm not sure what IPMC stands for. But otherwise, do you think, I guess if I rephrase is, do you think these tactile sensors will they find their way into applications?
Yeah.
I think that's what he means.
Yeah, so I think they will, because so we go towards, I think, it's a kind of a technological world where we need a lot of information, and we can make sense of a lot of information with a lot of automated devices. But of course, like the application I showed you, for example, was an application where the system is blind, essentially, so it doesn't have any visual information. And this is not a case that we will have in the future, because we have a vision that works very well, I would say, for maybe 80% of the tasks. So tactile sensors, I think, aim to kind of improve the performance in the remaining 20% of the tasks. So the next steps would be, for long-term research, would be like, how can we integrate multimodal sensory information, so from visual and tactile sensing, make it in a very efficient way, or in a way that it generalizes to the different approaches.
That sounds great. I have a related question. Do you know what accuracy you actually need in tactile sensing, or how the accuracy that you get compares to what humans have?
Yeah, so in terms of, so I think that the most relevant feature that is usually like discussed when you talk about the human sense of touch is the spatial resolution. So how can we discern touch over a surface? And the fingertip of humans has a resolution of about 1.5 millimeters. That's why we chose our discrete bins to be 1.6 millimeter side. What was the second question again?
I guess my question is, how accurate do you need it to be for a task to be successful?
Yeah. So it depends on which task. I think for the swing up is relatively is relatively important, in the sense that you need to capture the trends, but probably the exact value of force is not very relevant. For tasks such as state estimation, if you want to estimate, for example, the position, the pose of the pole by using the force readings, I would say, use the torque and the force to do forward dynamics. Then you need this to be very accurate if you don't have any other information that about the position or the angle, for example.
Okay, great. I see one more question in the chat, and it's specific to your learning. For the count pole randomization, is it done uniformly, or is it adaptive over time to make policy learning more robust?
Yeah, it is done uniformly. So no, we really do it uniformly in a fixed range. We haven't pushed too much this range, although like the poles that we used are very different. Yeah, we haven't explored adaptive sampling. I think this would be an interesting direction as well.
Great. And one question from me: if you compare your tactile sensors to others, what are the advantages or disadvantages of your current design?
Yeah, so the advantages, I think, are the fact that the sensor is very easy to manufacture on the hardware side, and on the processing side, we have shown that we can extract very accurate distributed forces that help us also in planning next tasks, next steps of the tasks in a robotic setting. Compared to other sensors, I am thinking, for example, gel sight, which is kind of the state of the art that often is compared with. Gel sight is usually more of a deformation sensor, so it can sense the deformation, and the shape of the object in contact very neatly and in a very elegant way. Although then making use of this deformation information for robotic tasks is hard, because it's hard to make a model, right, of how to use the shape. Let's say, we believe that it's much easier to have forces and then use physics, essentially first principle models for planning. So in our case, we cannot estimate the deformation in such a fine and precise way, but we can estimate distributed forces for the task that we were aiming to solve.
Okay, yeah, great. Yeah, that's really interesting. So I guess that connects to one more question I had, and that is related to using prior knowledge versus learning. And you kind of really interlace the two in multiple places. Can you say something about how you came up with that type of design of a mix of prior information and learning?
Yeah. So that's a very good question. So I think, yeah, I believe that there are things that are very difficult to model, for example, soft materials. And if you want to achieve high accuracy, high sensing accuracy, I think we're still very far away from doing it in a model-based fashion. You know, like there has been research in continuum mechanics for ages now, and FEM simulators are still very slow if you want them to account for the actual physics of the problem. So I think it's kind of very optimistic to say now we have more computing power, we're going to solve it soon. It's still far away. So why don't we isolate this problem with a data-driven approach, and then still get out physical quantities, and then use the physical quantities to use them first principle methods, for example, for control or for estimation. Because there, if we have a contact with a rigid object and we know the forces applied on the rigid object, then we can use classical methods. So that's kind of the idea here. Like we isolate the difficult part of the dynamics from the easy part of the dynamics.
Yeah, that sounds really interesting and makes sense. Yeah, let's finish maybe with the last question, and then we'll thank you for your time. What is next? Like, what is the immediate next thing you are tackling?
Yeah, so I think this the fact of having a lot of sensor information is kind of an unknown task in control. We don't know how to make sense of all this distributed information. For example, we did it in a reinforcement learning fashion. So is there a way to make use of it more in a more principled way, less of a black box way? So the second question is, can we use distributed information for state estimation? Because if we manage, for example, to fully estimate the state of the pole, again, we can use classical methods, which are very well studied once we have the full state of the pole in the swing up case. For different applications, we are also exploring whether we can detect slip detection in a principled way. Most of the time it's done in a learning-based fashion, which means we collect a lot of data and label them usually manually, because it's hard to detect slippage, if not with human intuition, maybe with cameras, but only when it's too late. So if we can do it in a principled way using forces, if these forces are accurate, it would be great, because it means generalization to all bunch of different contact objects.
Great. Okay, thank you so much.
You muted, I think, for a second.
Thank you so much for the talk. We'll give you a quick break, and then you have a few more individual meetings. So everyone, please let's thank Carlo for this very interesting and broad talk from hardware to learning. Thank you so much.
Thank you. See you.